Okay. So, welcome everyone. We are moving on to integration. So we are going to leave the stats for a bit. Our plan for the rest of this term will be, we've got two tests that we're going to get through. They're both short, sharp units. We have rules of integration, so chapter 4, it will take us 2 or 3 weeks. And we have applications of integration, which is about the same, 2 or 3 weeks. They're both short units, and we have a test on each of them. And they'll both be done. Historically, they've both been done right before the end of, so we'll have one in 3 weeks and the other one right before the end of term. And then we have a decent break, come back term 3, ready to start continuous random variables, which is our last unit of statistics. The other thing to say is that our assignment, so our one assignment, is on the applications of integration topic. So we will be starting the assignment late in the term, around week 8 or week 9. I'll hand it out, and it is very much an individual task. There's lots of resources online to get you started on the assessment task there. So we'll keep that in mind. That's our plan for this term. We've got a few interruptions coming up and so forth. We've got public holiday, and then we've got a couple of student-free days there. So let's get straight into 4A.1. We have consider the equation. Maybe I'll just talk about chapter 4 as well. The textbook does a really poor job, I think, in ordering it. So that, what I've listed there, that's the order we are going to do this unit in. You'll notice we don't do exercise 4B, and we do 4C right at the end because it goes really well with 4G. So we're going to do 4A, then we're going to skip to 4D, all right? And then we've got E, F, C, G. That's the order we're going to do it in. Okay, here we go. We've got, consider the function y equals 2x plus 1. Sketch the function over the interval from 0 to 2. So this is the equation of a line, and we're going to sketch it manually. We're going to recap some of those skills. So just in terms of my Cartesian plane, I'm going from x is 0 to x is 2. All right, so that means the y values I'm interested in. When x is 0, the y value is 1. So that's the first point that we'll have y is 1. And then we'll have when x is 2, the y value is going to be 5. So my y is going from 1 to 5, and my x is going from 0 to 2. So that's helped me to discover over what domain and range I should graph this function. Okay, so this function has, we've got when x is 0, we've got x is 1, and x is 2. When x is 0, the y value is 1, so that's the first point that it passes through. When x is 1, the y value is going to be 2 plus 1. All right, 2 plus 1 is 3, so that's going to be here. And when x is 2, the y value we've established already is 5. This is the equation of a line. It has a slope of 2 and a y-intercept of 1. Y equals mx plus c. The y-intercept is 1. The slope is 2. What does a slope of 2 mean? It means, so if we have slope is 2, always think about slope as a fraction. It's changing y on changing x. It means as you go across 1, y goes up 2. Across 1, up 2. Across 1, up 2. There's our equation of the line, sketched beautifully. Part A complete. Okay, now, what we're doing within integration, we're going to be finding the area under the curve, and we're going to start by using a few fairly primitive techniques. So the first one says, find an approximate area using 2 upper and 2 lower rectangles. Okay, let's start with lower rectangles. What I'm going to do, I'm going to draw 2 rectangles under the curve. There's one, and here's another one. Find an approximate area using 2 lower and 2 upper rectangles. So the area of these rectangles would be an approximation Okay, so it's an indication of this area under the curve, right? Between 0 and 2. Okay, now who can tell me, is it going to be less than this area, more than this area, or the same as the area under the curve?
Less.
It's going to be less than, isn't it? Because we've got all these gaps that we haven't included. Okay, so this lower rectangles, the lower estimate of the area is going to be less than the actual area. Okay, let's go about finding the lower estimate. So let's call it the area using the lower estimate. All right, so the area of a rectangle is just its base times its height. So my first rectangle has an area of 1 times 1. Okay, my first rectangle is 1 times 1, and my second rectangle is 1 times 3. Okay, so this gives me 1 plus 3. My lower estimate is an area of 4. Okay, next let's do an upper estimate. Now I'm going to sketch it again. Okay, from 1 to 2, here's 0, here's 1, here's 3, and here's 5. All right. Now, for upper rectangles, they are drawn above the curve. So here's the first upper rectangle, and here's the second upper rectangle. All right, and I'm going to rub out the one I'm sketching over the top of. Okay, now, is this going to be above, below, or the same as the actual area? Above, right? Because look at this overestimate. Look how much we've gone over the curve. So let's go. The area of the upper estimate, all right, is going to be 1 times 3 plus 1 times 5. This gives us 3 plus 5. This gives us 8. So we have a lower estimate of 4 and we have an upper estimate of 8. All right, so what this means is we can make a statement about the area. The area lies somewhere between 4 and 8. Okay. So, the next question says, make a conjecture, make a guess. What will happen to the interval? What's going to happen to this interval if we increase the amount of rectangles that we use? So we only used 2 rectangles and you can see there was a lot of waste. All right? Next, we're asked to use 4 rectangles. So if I'm going to draw 4 lower rectangles for you. Okay, there's 4 rectangles. So we've doubled the amount of rectangles we've used. What can we say about this estimate compared with this one that we had here? Is it going to be closer to the actual area or further away from it? Or is it going to be the same answer? What do we think?
Closer.
Closer, isn't it? Because we've gotten rid of some of the error. Before, we had that much error included. And now because we've got more rectangles, we've gotten rid of that error. Okay? So let's go through quickly and let's do the lower estimate now using 4 rectangles. Okay? So each rectangle has a width of 0.5 now, doesn't it? The width is 0.5. And whenever we want the y value is just equal to 2 times the x value plus 1. So the y value here is 2 times 0.5 plus 1. 2 times 0.5 is 1, 1 plus 1. So the y value there is 2. So we've got 1, 2. 2 times 1 plus 1, the y value there is 3. All right, and so on. 4, and then that has a y value of 5. So now our lower estimate, okay, is going to be 0.5 times 1. That's our first rectangle, 0.5 times 1, plus 0.5 times 2, plus 0.5 times 3 for the third rectangle, and plus 0.5 times 4 for the fourth rectangle. Now, whenever you're thinking about these calculations, okay, the width of each rectangle is the same. The thing that changes is the height. And so we should think if 0.5 is the same every time, 0.5 is a common factor. I can just pull it out the front. Okay, and then what am I left with? I've pulled the width of the rectangle out the front. I'm just left with the heights of the rectangles. 1 plus 2 plus 3 plus 4. Okay, what's that give us? 3 plus 3 plus 4 is 10. Half of 10 is 5. Okay, so now, based off, we're using 4 rectangles, we have an estimate, a lower estimate of 5. Let's get the upper estimate using the same technique. All right, so I'm going to draw these triangles on here. We'll have that one, that one, that one, and that one. All right, maybe I'll get rid of these ones so we don't have to look at them. Okay, and let's do this upper estimate in one go because we're smart people, and we know that 0.5 is the width of all the rectangles, so we're going to factorize that out the front, and then we just have to add the y values of the rectangles, the height of the rectangle. The first rectangle has a height of 2, then 3, then 4, then 5. So we have 2 plus 3 plus 4 plus 5. So what's that? 14, and half of 14 is 7. So now our area is between 5 and 7. And so we've demonstrated that the more rectangles we use, the closer and closer and closer our estimate is to the actual area. All right, the actual area, our first estimate was pretty rough. We only used 2 rectangles. It was somewhere between 4 and 8. But we saw when we doubled the amount of rectangles, we decreased the area. We became more certain of where the true area lies. Okay, so what we're doing in integration then is we can conjecture, if I used 4 rectangles, it was close. What if I used 100 rectangles? What if I used 1,000 rectangles? And so you can see what you're doing there is minimizing the error and becoming closer and closer and closer to a true understanding of the area. Part F, find the solution using a geometric answer. Now, because this is the equation of a line, we can actually just solve this making a geometric argument. So I'm going to do that with you guys now. What we have is a composite shape. We have here a rectangle and a triangle. And so that means this area under the curve can just be described as a rectangle plus a triangle. So let's go through and make an answer for the geometric argument. We're going to have the area equals the triangle plus the rectangle. Now the area of a triangle is always half the base times the height. Half of the base times the height. That's the area of a triangle, and the area of a rectangle is just the base times the height. Okay, let's do the rectangle first. The rectangle here has a base of 2 units and a height of 1 unit. So the rectangle has an area of 2. Okay, 2 times by 1 gives me the area of that rectangle. The triangle also has a base of 2, but it has a height that goes from 1 to 5. This is 1, this is 5, which means the height of it is 4 units. There are 4 units between 1 and 5. All right, so half of 2 times 4 is 8, and half of 8 is 4. And and 4 plus 2 is 6. Now, what you notice, okay, so that's the exact area under the curve. The exact area under the curve is 6, and 6 lies exactly halfway between our lower and upper bound, okay, between our lower and upper estimates. Now, this will only be the case when you have the equation of a straight line. It will not work for when we have curves, all right, unless they're symmetrical. It's only the case for a straight line. Okay, so let's go through question 2. I'm going to do the lower, and then I'll get you guys to do the upper estimate. Okay, this notation, integral 0 to 2 of x squared. Okay, what that means, the area under the curve x squared from 0 to 2. All right, so if we sketch the function y equals x squared, it looks like this. All right, it's a parabola, and we want to know what's the area from 0 to 2 again, and we're using 2 lower rectangles. Okay, so lower rectangles means we take the points below the curve. So my first rectangle actually has a height of 0. And here's my second rectangle. Now remember, if you want the y value, well, the y value is just equal to the x value squared. All right, so the y value, when x is 0, 0 squared is 0. When x is 1, 1 squared is 1. When x is 2, 2 squared is 4. That's going to be up there somewhere. Okay, that'll pop in when you're doing the upper, when we do the upper rectangles in a moment. So our lower estimate then, all right, each rectangle has a width of 1. So the first rectangle, 1 times 0, has a height of 0. Okay, the second rectangle, 1 times 1. So our lower estimate is 1. Okay, we'll do our upper estimate. I'll sketch the curve again. From 1 to 2. So upper estimate means we're sketching the rectangles above the curve from 1 to 2. So we've got our x values here. This is a y value of 1. Okay, 1 squared is 1. This is a y value of 4. This 2 squared is 4. So the first rectangle is 1 times 1, and the second rectangle is going to be 1 times a height of 4. So our upper estimate now is 5. State an interval for the area. The area lies somewhere between 1 and 5. Okay. So let's get you guys to make a start. You're going to try this with, let's just do question 1. I don't want you to worry about question 2. Pull out, let's do question 1, and then we'll have a look back up here together, and I'm going to show you some online software that we're going to use and experiment with for the rest of 4A.1. Okay, so start with 4A.1, question 1. I expect this to take us about 5 or 10 minutes, and then we'll come back together to have a look on the screen for some online software that we're going to use to help us answer some of the other questions. Question 2, if you want to do it, you can, but you don't need to. It is quite a challenging question.